You were a
Dude, it's like
media.
yesterday I went up to your phone. It's like if you or like I am recalled. Yeah, pretty much. Basically,
I should ask. Orange binder and a black binder.
Mine would be better.
My binder's whatever. Orange binder and black.
I know mine doesn't either. I have like a side thing.
Mine does. It doesn't look nicer for the lab.
Yeah.
Okay, so we're switching, we're gonna do the same concepts that we did the last, like, 2 weeks as far as, like, tests and intervals, 1 sample, 2 sample. But we're gonna do everything with means now, means or averages, where before it was always proportions. So that we use a different distribution instead of a normal distribution, it's called a T distribution. So you use T for problems involving means, averages, and you use Z or normal, that's what we've been using for problems involving proportions or percents. So a T distribution is pretty similar to a normal distribution. It's still approximately normal. The center is still the sample mean, I'll put, because I don't know if we're doing 1 or 2, as long as it's random. No, we don't need that sign. And then the idea is, if I let's fill this out first. T distributions have a larger standard deviation than normal curves. So I don't know, like if I take a sample mean in here with you 20 people or whatever, and I try to apply that to a big population, I know your standard deviation, like the standard deviation of my sample, but I don't know the standard deviation of like the big picture. And think about it, like if I knew the standard deviation of the big picture, there would be no reason to take a sample, right? Like I'm gonna randomly try to figure out, I'm gonna sample 100 people to see who's gonna win the election. Well, if I already know the population information, I already know the result, so there's no reason to like do a procedure. So if I only know the sample standard deviation, I kind of have to guess at the population standard deviation, and you need like a little extra room for error because you're guessing. So your T distributions are gonna have a bigger standard deviation, they're gonna be like wider. So this is because we are estimating the population standard deviation. Because we don't know it. You can hear me.
Oh, you did right that much.
I did write all that, yeah. I was always afraid that at some point in my academic career, some teacher would just like talk, and I had to like just take notes. Like there was no forum. They wouldn't stop and wait for me. They would. I don't know, I feel like you're kind of conditioned to expect it. Does that happen in any of your classes? Like the teacher just talks, and you're just expected to like note on things they say on your own. It like never happened to me. I was always afraid that was gonna happen, but it never happened. I don't want to name names. Okay. The larger the sample size, the closer T distribution distributions get to a z distribution or a normal distribution. So as you get a larger sample size, you have to estimate less, so your standard deviation becomes closer to normal. This might make more sense when I start drawing these. So let's do these first. Let's find the confidence intervals. So grab your calculator. And you're able to kind of see how it approaches things, I guess. So for t sub 10, this is supposed to be a t interval. I couldn't get it to do the sub, like in the cell. This is supposed to be a t interval. It's really supposed to be like that. A t interval with a sample size of 10. So what that means is the degrees of freedom, it's called, is 9. You don't really have to ever know what degrees of freedom is. I can explain it at some point. I don't want to do it right now because it would get lost in what I'm actually trying to teach. But it's just one less than the sample size every time. So degrees of freedom is n minus 1. So this is supposed to be T50, which means the degrees of freedom equals 49. This is supposed to be T99. I'm sorry, T100. Degrees of freedom is 99. So the number at the bottom there is the sample size, and then the degrees of freedom is always one less. Alright, so hit second, no, hold on. Hit second distributions, so second vars, it's like the distributions.
Do you have any working ones?
So second distributions and then inverse t. So number 4 is inverse t. Does everybody have it? Like, there's a couple calculators I've seen that randomly just don't have inverse t. The TI-83 is the one else. Okay. So hit that, and then you do the same idea. This is 90%. So you're gonna do 1.9 divided by 2. That's the same thing we did before, right? For like a z star thing. Degrees of freedom is 9, so you don't put the sample size, you do the subtraction of 1 first. And then hit enter, then I get 1.83. So go put that in your chart, and we're just gonna watch what happens as the sample size gets bigger. So do it again, but now your sample size is 50. I get 1.67, I guess 1.68. And then do it again with 100. So just change your degrees of freedom to 99. Or you can just say like second enter and it'll do instant replay. Edit, whatever. So that's 1.66. Everybody get what I'm getting? Are we finding it? We're okay? Alright, so now so those are all t's. Now I want to do inverse norm. So inverse norm is a z statistic. But my claim is that the t statistic gets closer and closer and closer to z as our sample size gets bigger. So we should be, our z-score I'm going to guess is like 1.65, 1.64, because it's getting closer and closer and closer. So do inverse norm of 1.9 divided by 2. Yeah, that's like 1.645, 0.65. So z doesn't have degrees of freedom. You don't need a sample size for z's. These were inverse t. That's inverse normal. And notice that these numbers get closer and closer and closer. If I did like T sub 1,000, it'd be basically the same thing. So the more data you have, the less you have to guess, the less it looks, or the more it looks normal. So if you have to sketch these, and these are fairly common, kind of maybe multiple choice questions, you should probably watch me draw it first and then draw yours. So let's say this is a Z, or like a perfectly normal curve. So that's Z. Well, T sub 100, that's a pretty big sample size, so it's pretty close to Z, but not quite. So it'd be like a little more room in the tails, a little shorter, and it's just like a little more spread out. So that might be what T sub 100 looks like. And then that just kind of keeps happening, that pattern. So the next one, draw like a different symbol here. So maybe like, we'll do like a little twirly. So a little more room in the tail, not quite as tall, more spread out. So that would be like what T50 looks like. And then T sub 10 is going to just like, it's smushing the normal curve even more, and pushing things out to the tail. Yeah, so I'd do like a heavy dashed line, I guess. It looks something like this. If you had different colors, that'd be ideal. And that'd be like your T sub 10. So small sample size is really wide and kind of short, and then as you get a bigger sample size, it like pushes in from the tails and gets taller. So if I were to say like which one of these has the largest standard deviation, what would you say? So your possible answer are 10, 50, 100, or Z. Which one has the largest standard deviation? Which one of these is the most spread out? The biggest portion in the tails is the 10. The smallest standard deviation is the one that's like packed closest together. That would be your Z. Alright, I want you guys to try to do what I just did over here, but with the 95%. drawing sucks too, but like, can you tell what's happening? That the Z is here, and then as the sample size gets smaller, it just like to shove things to the outside. Okay. Sorry, are we good with this? Or sorry, wait a second. Is anybody still writing anything on here? All right, we're gonna do a one sample t-test. So I'm gonna do like an example and then a template. So if you want to grab, I don't know where you guys are keeping these. If you want to grab a sheet of paper, if you put them in your notes. But you know, we have the z-test, two sample z-test, z-interval, two sample z-interval. We're gonna do all four of those things with means. So if you want, I don't know, however you organize it best. But if you want paper, come grab some paper.
Oh my god, yeah.
I couldn't follow it. I don't think so. Then again, I really feel all it's hard to do. I don't know. Like I keep looking at you, and it doesn't look like the right shape, but it doesn't look dark. Also, that's what happens. You sound like
We're at it. I was like, she started asking me that. I know.
Okay, so this is your calculator just says t-test. It is one sample, but your calculator just says t-test. So you can call it a one sample t-test, you can call it a t-test. And this is for means, not proportions. How do I know it's for means and not proportions? Because it's t. That's like the whole point of t. Okay, so we would start off by, like before we would say p equals the true population proportion of whatever, but now we're dealing with means, so we're going to say mu equals, actually I should probably tell you what we're doing, because it's an example. So let's say I think that Pepsi is not, wait, hold on. Pepsi or Coke? Raise your hand for Pepsi. You're trash. Raise your hand for Coke.
My bad.
Okay. We're going to do Coke, because Pepsi sucks.
Sorry.
But I think,
I'm serious about this. This is
shh. Just don't start crying.
important.
The, too soon? Too low? Too soon? Too low?
That's crazy.
Sorry.
Crazy thing to say.
It's not too.
I think that Coke is screwing us over. They're not giving us 20 ounces in a 20-ounce cup. So this is going to be the true population. Mean ounces in a Coke bottle. Because, you know, if they could put like 19.8 in there and say 0.2 ounces over billions of cans, that would make a big difference for them. Then you're going to put the HO and the HA. So like HO is the initial claim. So we would assume that the mean is 20. And then like we are suspecting that they're not putting as much in there as they claim. So our HA would be mu is less than 20. And let's say that I gave you, we did a sample size of 100. Our X bar came out to 19.8. And our standard deviation, that's the standard deviation of X bar, let's say it was 0.5. Alpha, if I didn't tell you what's alpha, 0.05, let's just say it's 0.05. And then we can do conditions. That's like our intro. So then it's the shape, center, spread stuff. So the shape, and we gotta remember back to before we did proportions. The shape is approximately normal in this situation, based on what I've given you. Can anybody tell me why? So it's not like the 10 successes and 10 failures, or the NP and the NQ anymore, because there is no P and Q, there is no success and failure. That's proportion. N is greater than or equal to 30, was one way we did it before, and that's true here. If it wasn't greater than or equal to 30, what else did we talk about before? Anybody? Bueller? So if it says the population is normal, that's another sign that you can use, but we can use that, and we'll get into that in the template. But right now we can say approximately normal because N is greater than or equal to 30. Center. Wait, I have to fix something before we do the center. Go back up here and write SRS. Now we're good. The center is going to be 20, since SRS. So we would assume the mean of our sample is the mean of the whole population, as long as we did randomness, and we did. And then spread independent. This is the 10% thing that we need. So I'm fairly certain that 100 is less than or equal to 10% of all Coke bottles. Well, I feel bad. I'm concerned that I went too far. I apologize.
Yeah, it's a horrible thing to say.
You were the worst person.
I'm just kidding, no, it's okay.
Yeah, it was, I could see you saying that. I could also see you laughing. I wasn't quite sure where it was going. I probably just should have said it.
I hope you know I'm never gonna forget that.
Okay. That means you'll remember me.
Just kidding.
Okay, test statistic. So we did this last time too, but it was Z's instead of T's. So now it's a T, equals statistic. Where do statistics come from? Samples or populations? Samples. Minus parameter, which comes from the population, divided by the standard deviation. So in our case, that is X bar. Remember, we gotta write it in words, and then you gotta write it in symbols, and then you gotta write it in numbers. So we're going through like all three levels. So there's your words: statistic minus parameter over standard deviation. Statistic is the sample mean, that's X bar. Parameter is the population mean, that's mu. And the standard deviation, remember, is the standard deviation divided by the square root of n, because you took a sample. This was back in like the chapter before the proportions. When you have a sample standard deviation, you have to divide it by the square root of n. And then you put in what we know. So X bar is 19.8. So that's, a little less than 20. The question is, like, is it enough less that I'm convinced something crazy is going on, or is it like, yeah, I can't really say they're lying. The standard deviation is 0.5 divided by the square root of the sample size, and divided by the square root of 100. So divided by 10. And then you're not gonna like calculate that. You're gonna go to your calculator and it's gonna tell you everything from there. Questions on anything yet? Like, this should feel fairly familiar-ish because we've done like the process and you've done mean before. We're just kind of putting new stuff with it. But go to your calculator. Stat and then tests. And then t-test is the second one. We good? So then it's gonna say, so we can do this two ways. If I had the data like in my calculator, like say I had all the list of all the values in L1, I have like the summary statistics, so that's what I'm gonna put in. So that's the mu naught, so whatever the H naught mu was, so 20. Who's lost? Can I help someone? I heard someone say test. Who do you need help finding something? Okay. X bar is what we got for our sample mean, so 19.8. Standard deviation is 0.5. You don't have to put like the divided by square root of n here, because you're going to tell it n and it's going to do that part for you. Sample size is 100. I want the sign or the arrow to point the same way it does in my HA, so that's a less than. This should be a less than. And then you can do calculator draw, and like from here it's really similar to the last. So I need to zoom stat, because that's doing some other weird. I don't know what that's doing. There's what I was looking for. Okay, so t is -4. What's the p-value? Did you get 0.0006? I got 4.
Yeah, 0.999. I think you put it as greater than instead
No, I think you put it as greater than. There's less than.
Mu naught is less, when you click that.
So what's that?
20 is mu naught, right?
Yeah, and we think that we're less than 20.
So the alligator would be E.
So it would be the other one.
No.
20 is mu naught.
We think
Oh,
mu naught is
never
20.
mind, never mind.
We think our
Surely on the,
samples.
Yes.
There's too many.
So I'm talking about eating things. We're not second
Alligator
things.
gets-
I think we could do better than that.
What?
I don't think we should do better.
That's fine, okay. But are we good?
you gave up just like that.
I know,
You're like, fine.
I was like, I don't really care
Should
that
we do,
much.
alright, you know what?
But I'm concerned that like you're getting 6 and I'm getting 4.
I'm getting a 6 too.
6.112576.
I got the negative. I'm not getting a 6. I'm getting a
-5.
I'm getting
You have this data in here and you're getting a different number than I am?
There he goes.
I'm getting
What do you click when you put calculator? Because then
That's
you're
like
gonna
exactly
see
what I
that.
got.
Maybe it was like the graph. So I do get 6 on this. Maybe the graph was like screwed things up. Okay, so the p-value. Are we getting this? We're good?
Yeah.
Okay. I just want to make sure we understand that's like scientific notation, right? So the p-value is 0.00006. But again, we have to like pretend we don't know that and kind of jump through the hoops of finding it. So we're gonna make our little sketch. So mu is 20 is in the middle. I got 19.8. My t is, we used to write like z equals whatever. Now we're just gonna put t equals whatever, so t is -4. Am I gonna be shading to the left or to the right? To the left. Why? Because we're looking at less than. So the less than direction is to the left. And then we're gonna be like, hey, we know how to find the p-value. So it's t-CDF. There's a normal CDF that we used to use, because that's what z is in normal. There's a t-CDF. It works the same way, except you have to put the degrees of freedom at the ends. But as far as like the commas and stuff, so what's my left-hand or lower boundary here? -9999. What's the upper boundary? -4. And then you're gonna tell the calculator, 99. If you are on a written AP portion, you put degrees of freedom there so that they know that you know what that is. And then we should get this number that we have, but let's like make sure we can do TCDF in our calculator and get the same thing. So go to the distributions again. Second bars. So TCDF is number 6. You'll never use TPDF. And then it works the same as the other one, except now you get degrees of freedom. So -999, -4, degrees of freedom is 99. I think probably some of you get that menu and some of you don't. So if you don't get the menu, it should look like that. And then there's that p-value that I got before. So that gives me 0.00006, which is basically 0. And at that point, if you got like 4 zeros, you can just say it's 0. And then we do our conclusion, which works like the same way as it did in the other ones. So that's obviously less than alpha, right? 0 is less than like any alpha you can get. So since our p-value is less than our alpha, we what? I think some people whisper it. Reject. We reject HO. This is far enough away from the center that I'm pretty convinced something. I don't think that's actually the true center. This is so far away. So I do think that Coke is trying to screw us over. So that was weird how I like advocated for Coke and then I said I would screw us over. Kind of just backstabbed myself. So we reject HO. The test is statistically significant. Just give it a sense. Do suspect AJ is true. Questions on that anywhere? Does that seem like not too bad because I think it's similar to the last stuff? 0 people shook their head up and out, left or right. Did you? Okay. I didn't. I take it back. I think. Is it about? Do you guys? Would you rather do a template or like another example that you try? Template. Okay. Let's do template. So t-test, 1 sample, template. So this is for means. So you start off by like identifying what we're working with. So mu equals the true population mean whatever. Put your context in. And then you'll have HO always has to be mu equals something. It's always a claim that, hey, this is what it is. And we're going to try to show it's either greater than, less than, or not equal. So HA could be less than, greater than, or not equal. past when this is like, they said 20 ounces of Coke, we thought it was less, and that was our alpha significance level. So then shape, center, spread. So shape is a little bit more involved in this one than it is in the proportion ones. There's 3 things that you could have, and if any one of these is true, you're okay. So 1 would be n is greater than or equal to 30. So you look for that first. If you got 30 or more, you're golden. You don't have to worry about the next 2. If it's not greater than or equal to 30, then you look for a normal population. So if I had said like the ounces in a Coke bottle are normally distributed, like we know that for a fact in the big population, then we're okay. 90% of the time you'll have one of those 2 things. Every now and then there's this other situation they'll give you which is the most annoying for you because it makes you do extra work. If it doesn't tell you it's a normal population and you have a small n, say it's like 10, you have to do like a dot plot. And the dot plot has to show no skew or outliers. And you don't have to do anything like major. It's not like a fancy dot plot. They're not looking at labels. They're not looking at, like really it's just gonna look something like this. And you're just gonna go, hey, no skew or outliers. But again, 90% of the times it's gonna say one of the first 2 things. But we will do a couple examples of that. So the center is going to be mu equals x bar, no, sorry. Center is going to be mu as long as we have randomness. So we assume that the center of Coke bottles is 20 as long as we did it randomly, because the population means 20. And then spread. And what you're doing here is showing things are independent. That's that 10% thing. So your sample size is less than 10% of the capital N population. Those okay? Like, can I move on, or are we still ready? Alright, so then you gotta find the T statistic, but you gotta start off general, so with the words and the symbols and the numbers. So T equals test statistic. It was Z last unit. Why was it Z last unit? Because we were dealing with proportions, percents. It's T this unit because we're dealing with means. But then the fun part happens after, when I give you a problem and I don't tell you if it's means or proportions, and you don't know what unit we're in, and you have to like figure that out. It's not that hard. So you're gonna have the statistic minus the parameter over the standard deviation. And then you plug in numbers. And then you'll get your T. So I'll go through all 3 of the possibilities. You might get, over here, T equals negative something. This would be a less than situation. So if your HA was less than, you're not every single time, but you're very, very likely to get a negative T. Your p-value is this region over here. And we would find that by saying T CDF -999, up to t, and then tell the calculator the degrees of freedom. And that equals the p-value. So just like before, we have a negative z, we did normal because it was normals and z's go together. We said normal CDF, -999 to z. We didn't have to say the degrees of freedom, but it was the same idea. If it is a greater than test, basically the exact opposite happens. You'll get a t-value over here. It'll be positive. You'll be shading to the right because greater than means above to the right. And then the p-value would be, what's your lower boundary here? T, your upper boundary. 9999. Good. And then the degrees of freedom. That's your p-value. Last. And then the third situation, it could be a not equal to. So remember, you'll get one of the t's. Depending on how the problem is set up, you'll either get the positive or negative t. It's your job to know, wait, this is a not equal to, that means it's a two-sided test. That means I need to do the same thing on the other side. And then for the p-value, remember we talked about, you could do this part, so like DCF -999 to t and then double it. You could do this part and then double it. I think that's probably the two easiest. So I'm gonna do 2 times. It doesn't make a bit of difference which one I do. I'm gonna do the left one just a little closer to it. -999 to t, comma degrees of freedom, and then that is your p-value. So again, the concept is the exact same as with proportions, it's just we're learning this new t thing instead of normal / z. Alright, then we do our conclusion. So there's 2 possibilities. So you would say, one option is like since p is less than alpha, and this doesn't change from the last unit. There's kind of 3 things we say. So we reject HO. The test is or is not statistically significant. It is statistically significant. I found something significant, right? I found out that Coke was lying to us or whatever it was. We do suspect HA is true. Did we prove it? No. I still could be wrong. Is that like type 1, type 2 error? I'm probably right, but I didn't prove it for sure. Like the Coke bottle thing, even if, let's say I randomly sampled 20 bottles of Coke and they were all exactly 20. Does that prove that every single bottle of Coke is actually 20? No. I mean, it makes it like more likely, but it doesn't prove it. So your alternative would be since P is greater than alpha, that would be we failed to reject HO. I wanted to call you a liar, but I was not. Sadly, was not able to. Test is not statistically significant. You do not suspect HA is true. Could HA be true? It's possible. There's a small probability of that. That gets into the type 1, type 2 errors thing from last week, which we'll practice more too. We suspect. Alright. Any questions I can answer? Does that seem like overwhelming or okay?